Yeah. So welcome to our the IAMAS Early Career Scientist special event. So this is the Asian edition. So we have invited speakers from most Asian countries like China, Korea, and Japan, Australia, to present during our conference. So first, I'd like to give a brief introduction of IAMAS and the IAMAS Early Career Scientist Committee. So we share my screen here. Okay, so the full name of IAMAS is the International Association of Meteorology and Atmospheric Science. Our president is now is Professor Joyce Penner, and I'm the chair of the Early Career Science Committee. And IAMAS is part of IUGG, which is the International Union of Geodesy and Geophysics. It is a non-governmental scientific organization and established more than 100 years ago. And for IUGG, there are many society or associations within IUGG, and the IAMAS is one of the associations. And the purpose is to promote scientific communication within the meteorology and atmospheric science community and the related fields. So also within IAMAS, we have 10 commissions. Each address a specific area of study. Like we have the International Commission for Atmospheric Chemistry and Global Pollution, and the International Commission on Atmospheric Electricity, International Commission on Climate, International Commission on Clouds and Precipitation, International Commission on Dynamic Meteorology, Middle Atmosphere, Planetary Atmosphere, and their evolution, and the Radiation Commission, and the Ozone Commission, and the International Commission on Polar Meteorology. So it well covers all the research areas within climate and atmospheric science. So now the IAMAS Bureau consists of 5 members. Joyce Penner is our president. She's from University of Michigan. And John Turner is the past president, and he is still serving in the Bureau. And Steve Ackerman, he's also from the US, as a Secretary General, and our 2 vice presidents are John Burroughs and Mary Scholes. So John is from Germany and Mary is from South Africa. So as you can see, we do not have many participation bureau member from Asia. So I hope that everyone in our region can increase your visibility in IAMAS. And the IAMAS Bureau will be meeting monthly to decide the day-to-day operations of the IAMAS organization. And also, last January, we formed this early career scientist committee. So to increase the participation or increase the role of early career scientists in IAMAS, because early career scientist is a very big community. So we hope we can involve more young people in the IAMAS activities. Then we have 10 members from 7 countries. These are our members, and each member will be representing an IAMAS commission. This is myself. Here I'm the chair, and Sarah is our co-chair, and she's representing ICCL. And also our 2 co-chair for today's events, like Fei Zheng here, she's representing the Dynamic Meteorology Commission, and also Yunzhu Li. Well, actually, she just left our committee, so she's still supporting our event. She used to represent ICPAE, and we'll have a new representative from that commission soon. And so if you would like to participate in IAMAS ECS activities, or you want to serve in our committee, we are very welcome. So you can just contact us. Yeah. So how to reach us is we have a website. This website is under the IAMAS main page. So this is the IAMAS main web page. And if you click about IAMAS, there will be ECS tag. If you click the ECS tag, you will be directed to our web page here. And also in the middle of the web page, join the IAMAS ECS mailing list. We have a mailing list, so you can join. You can just register with some of your information. The primary information is your email, so that you can join our mailing list and receive our activities. And also we have a Twitter page, which is the IAMAS Twitter page. This page is managed by Sarah, but she's on maternity leave now, so it seems this page is a bit outdated, but you can see the some of the past news and past activities on this Twitter page. Actually, IAMAS also has a Facebook page. It's not only about ECS, some ECS events are there. It's mostly about the IAMAS activities as a whole. So within our committee, we have several working groups. We have a webinar group. We have started a monthly webinar already, and also other groups like manage our website and social media. This I want to emphasize is we have started this monthly webinar series last June. So this special event is to celebrate our anniversary. So we have our webinar has been running for a year, and we have held 10 webinars already. Each represent one of our 10 commissions, and our speakers are all early career scientists. Well, we actually plan to involve more like senior scientists in our future webinar, and we also plan to have some regional or topic-based talks. We have a YouTube channel, and all these past talks are posted on this YouTube channel. So far we have made some progress in the past year. Our main progress is to start this the mailing list and the webinar series, and also we plan to have a big ECS event at our IUGG assembly next year in Berlin. This assembly is planned to be in person. So hopefully many people can go under this COVID situation. We are planning to have a ECS event before this assembly, and also a scientific session within this assembly. And these are, we also start to form regional working groups and some other webinar series. So these are brief statistics of our subscribers. So as you can see, there are many regions that are underrepresented by the IAMAS ECS mailing list, like in the mostly like Europe and some of the South America community. And this is the career stage. Most of our subscribers are postdoc and doctoral and postdoc students, and also some young faculty and research scientists. And by commission, we have the most subscribers from the climate and also dynamics and commissions, and also from the cloud and precipitation commissions. Yeah, so welcome to join us through our mailing list to receive our activities and events. Yeah, so thank you very much. Well, to save time, if you have questions, you can leave them in the Q&A or chat box, and I'll try to answer later. Yeah. So guess I'll stop here. Yeah, Thank you very much for your attention. And so now we'll officially start the scientific talks of today's event. Our first speaker is Professor Yi Huang from University of Melbourne, Australia. And she will be talking about the role of clouds in coral bleaching events over the Great Barrier Reef. Welcome, Professor Huang.
Thank you very much, Jing. Thank you very much for the invitation and introduction. So I really appreciate having the opportunity to present here at this event. So let me share my screen. Can you see my screen?
Yeah, very well.
Okay, excellent. So yes, I guess I've spent most of my time in the past 8 or 10 years or so looking at clouds and precipitation over the extratropical regions. But today I've actually decided to present some of the work we've been doing quite recently, trying to understand the role of clouds and atmospheric processes in the coral bleaching events over the Australian Great Barrier Reef. As we all know, that climate extremes are now becoming increasingly relevant under the context of global warming. And in fact, our latest IPCC report has identified the loss and degradation of coral reefs as one of Australia's key risks. So this is, really partly motivated by that. So let me first acknowledge the co-authors of my talk, including 2 of my PhD students, Estefania Montoya-Duke and Wenhui Zhao, as well as my collaborators, Stephen Sims and Mike Manton. So I think many of you, I believe, have heard about Great Barrier Reef, right? But perhaps not everyone knows that our Great Barrier Reef is actually the world's largest collection of coral reefs, making up about 10% of the global coral reef ecosystem. The Great Barrier Reef, as I show here on the map, is located off the coast of Queensland here in Australia. It's pretty huge. It's actually, large enough to be visible even from space. Unfortunately, as we know, the Great Barrier Reef and in fact the coral reef wall walls have been facing an existential, threat under a combination of pressures, and most notably the coral bleaching events. In fact, in the past 40 years, the Great Barrier Reef has already endured 7 mass coral bleaching events, and 4 of them were recorded just in the past 6 years. As we also know, climate change is the leading cause of the coral bleaching events. The evidence of the dominant role of the elevated SST or sea surface temperature in the bleaching process, particularly thermal coral bleaching events, is unequivocal. However, in addition to the sustained elevated water temperature, the solar radiation is also known to be a major contributor to the bleaching of primarily the shallow living corals. And that's because the intense solar radiation, which typically results from, prolonged periods of sunlight, can cause bleaching of the photosynthetic pigments even when the algae are not expelled. Right. So if you look at this bathymetry map, you can see that most of our corals in the Great Barrier Reef are actually located in the shallow water coastal areas where the water depth is only up to usually tenths of meters deep. So marine heat waves have been commonly recognized as a key driver of coral bleaching events. But on the other hand, I guess, it remains an open question as to what drives the marine heat waves themselves. So here in this recent study looking at the 2016 coral bleaching event using the ocean mixed layer heat budget analysis show that, the anomalous shortwave radiative heat flux associated with the cloud pattern shift under El Nino was the primary driver of the first ocean warming pulse of this event. Right, and this is followed by the contributions from latent and sensible heat flux anomaly, whereas the ocean kind of heat advection is playing a relatively minor role. In fact, there have been a lot of studies looking at ENSO and ENSO-related factors in relation to the core breaching events. But by and large, there's still a lack of understanding kind of within a broader climatological context. So in order to partly, address these knowledge gaps, I guess in the first part of our study, which has just been published in GRL, we use a newly available long-term cloud radiation satellite dataset, Cloud CCI, and RFI Fourier analysis to statistically quantify the cloud radiation SST relationship over the Great Barrier Reef with a focus on the coral breaching season. So in this paper, we looked at 5 coral breaching events that are well documented since the 1980s. The coral breaching season is defined to be from January to April, and we use ONI index to define the ENSO phases. So the key details of these 5 coral breaching events are shown here on this map, also in this table here at the bottom. I guess one thing you'll probably notice immediately here is that these 5 coral breaching events are, recorded under the various phases of ENSO, right? Including 3 kind of under El Nino, and 1 during the neutral phase, and also 1 here during the La Nina event. And this is quite consistent with the most recent coral breaching events that was just reported earlier this year, which occurred under a strong La Nina condition. So here I'm showing the special patterns of the cloud radiation SST anomalies during the 5 thermal coral breaching events. We've got the SST anomaly here on the top, the shortwave radiative flux anomaly at the bottom of the hemisphere here in the middle, and the total cloud cover anomaly here at the bottom. I guess one of the common features you already identified is that all these 5 events are characterized by a significant reduction of the total cloud cover over the Great Barrier Reef, and as a result, the enhanced shortwave radiative flux at the bottom of the hemisphere. If you look closely, you would be able to see that some of the most severe bleaching, as indicated by the stars, tend to occur in the mid and the subtropics of the Great Barrier Reef, and also tend to coincide with some of the area with the greatest cloud cover and the radiation anomalies. So in this work, we also looked more widely at the cloud and radiation SST relationships throughout the full time periods of the coral breaching season. And we want to understand how and to what extent these relationships are influenced by ENSO. So what we've done here is that we calculated the total correlations and partial correlation as well for between the anomalies of those variables, which I show here in this figure. There are a lot of panels here. I won't go into details, but I guess the key message I want to highlight is that we were able to identify a strong and statistically significant correlations between the cloud cover anomaly, the shortwave radiative flux anomaly, and the SST anomaly over the Great Barrier Reef shallow water area, so you can see here. And these correlations are strongest when we further consider a 1-month lag in the SST anomaly, most evidently in the mid and the subtropics. And this remains true even when the ENSO signal is removed, or in other words, these correlations are found independent of the large-scale ENSO effect. So having established these relationships, our next question, which is what we're actively working on right now, so this is actually work in progress, is to understand what atmospheric processes are contributing to driving these cloud and radiation anomalies during the coral breaching events. So once again, we look at the same 5 coral breaching events. We use the same definitions for coral breaching season and for ENSO phases. And we further look into, the contribution of the Madden-Julian oscillation, the variability of the MJO. Here, our MJO is defined using the real-time multivariate MJO RMN index, which include 8 phases that's defined in this Wheeler and Hendon 2004 paper. And also we use 42 years of Era 5 data to examine the atmospheric dynamic fields and also their anomalies. We also perform, the composite analysis for the anomalies. So here I'm just showing you some of the results from this composite analysis looking at the synoptic anomalies, primarily the wind and the pressure fields here during the coral bleaching events. So I guess one of the striking features you can see on these maps is that during these events, the Great Barrier Reef is characterized by this enhanced southeasterly trade winds, as you can see here, associated with a anticyclonic anomalies, which is part of the anomalous synoptic wave patterns that you can see here in the subtropics. And these anomalous synoptic wave patterns basically characterized by this anticyclonic anomaly that's centered over Southeast Queensland, pair with these cyclonic anomalies over Western Australia and another anticyclonic anomaly further to the west. And this pattern is most pronounced in the slightly upper hemisphere. So these anomalous synoptic setting really are known to be able to set the conditions that would be able to impede the penetrations of the tropical deep convections during this season. For example, the Australian summer monsoons. So that will lead to the reduced cloud cover over the northern Queensland as well as the Great Barrier Reef region. So how do these anomalies compare to those under the various phases of ENSO? Well, first here I'm showing the zoom-in image, which once again, we have the wind anomalies and also the SST anomaly in the background on the left, and we have the corresponding anomalies for the various phases of ENSO here on the right. So perhaps this is not too surprising. We see some similarity, between these anomalies occurred during the bleaching events and under El Nino here. For example, they both have these enhanced southeasterly trade winds, right? However, if you look closely, you see that under the El Nino condition, there is a lack of the well-defined anticyclonic anomaly that I just mentioned, as you can see here, in this composite analysis, right? And this would indicate that the synoptic processes may play an important role in driving the extremes of these coral bleaching events. And also, if we look more closely at the wind, here I'm showing the difference of the pressure field on the top and wind field at the bottom between the El Nino and coral bleaching conditions. You can see that these anticyclonic anomaly that I mentioned earlier also contributed to this even stronger southeasterly trade wind anomaly during the coral bleaching events, except perhaps in the inner reef. The reduced wind speed here may have indication in reducing the latent heat flux there, but overall, if we look at the outer reef as a whole, these enhanced trade winds would help drive the coastal downwelling due to the Ackermann transport, which would then reinforce the positive SST anomaly in this area. So as I said earlier, we also looked at the role of MJO and their variability in driving or contributing to the coral bleaching events. This is because MJO is known to be able to modulate SST in the tropical ocean and modify the local atmospheric conditions. So for those of you who may not be super familiar with the tropical climate, basically the MJO can be characterized as I show here in this animation, characterized by this eastward moving poles of cloud and rainfall along the equator, which typically occurs every 30 to 60 days, right? So here, the MJO diagram on the right is showing just an example of the evolution of the MJO RMN index for this period. So basically what this index does is that it divides the MJO based on their geographical locations into 8 phases, right? So each phase here representing an approximate location of the MJO around the globe, as I show here on this map. Right? So as a rule of thumb, the amplitude of the MJO can be approximated by the distance from the center of the diagram. So if the amplitude is less than 1 within this circle, then usually the MJO events are considered to be weak or not coherent. So here are the maps showing the expected difference in the cloudiness based on the position of the MJO during the coral bleaching seasons. So the blue shading here indicating the negative outgoing long wave radiation, or OLR anomaly, which is typically associated with enhanced tropical weather, enhanced cloudiness and convection. Whereas on the other hand, the yellow shading indicates the opposite, the suppressed condition of convection in the cloudiness. So climatologically, we can see that the MJO phase 4 to 7 typically associated with enhanced cloudiness over the Great Barrier Reef. We identify the reef here on the map, whereas the MJO phase 1 to 3 and 8 are associated with reduced cloud cover in the cloud study region. So what kind of role does MJO play? Here, we were looking at the frequency distributions of the various MJO phases during the coral bleaching season, which is indicated by the blue bars, and during the coral bleaching events indicated by the red bars here. And the numbers on the top are showing the mean amplitude for the corresponding results. So what we can see is that there seems to be a decrease in the active MJO phases during the coral bleaching period, except perhaps phase 5, but this is partly attributed to the weaker events recorded during this period. On the other hand, we seem to be able to see an increase in the inactive MJO phases, except perhaps phase 1. But as I indicated using a different red color, this is primarily attributed to a significant increase in the very weak events, right? So overall, we seem to be able to see some MJO footprints from the shifts in the MJO phase frequency distribution during the coral bleaching events compared to the climatology. And we seem to be able to see a more suppressed condition over the Great Barrier Reef during this period. So I guess to sum up, these are the take-home messages from my presentation today. And some of them, as I said, still work in progress. But overall, our study shows that the 5 thermal coral bleaching events are all characterized by a significant reduction of cloud cover and enhanced shortwave radiative flux over the Great Barrier Reef. And we were able to identify a strong and statistically significant relationship between the cloud cover anomaly, the shortwave radiation anomaly, and SST anomaly over the shallow water of the Great Barrier Reef. And this is independent of any ENSO effect. And we found that the cloud and radiation anomalies are associated with the southeasterly trade wind anomaly as part of the synoptic anticyclonic anomaly we identified there. And these trade winds anomaly could further induce ocean atmosphere interactions that would act to reinforce the positive SST anomalies. And finally, we were able to identify footprint from the large-scale climate drivers, such as ENSO, the intraseasonal variability, such as MJO, the synoptic process, as well as the air-sea interactions during the coral bleaching events, which suggests that the interplay of these systems are playing an integral role in driving the positive SST extremes there. So I guess with that, thank you for listening, and I'm happy to take any questions.
Thank you very much, Professor Huang. So since we have very limited time for question, I wonder if anyone wants to ask a question. Um, uh, I actually have one question here. So you mentioned the role of ENSO and MJO during the anomaly. So I just wonder if there are any connection between these two, like ENSO may also impact on MJO. So the phases, are there any difference in the like positive, negative ENSO phases?
Yes, I think you're right. I do think that there potentially some, positive, interactions between the different systems. And in fact, we have students there at Melbourne looking at, how the nature of the climate change due to the interactions of the ENSO and MJO. I guess the key thing is that we know the relationship is never linear. So, when one of the ENSO phase interfere with the MJO, then, it could produce something that's, different from when they're entirely separated. So I guess that's one of the areas we need to understand better. But for now, I think given that we have very limited samples, first of all, for the coral bleaching events, and we also have, very, limited data that can actually characterize natural variability of both ENSO and MJO. So it remains a challenge to understand how they interact exactly.
Yeah, it's a very complicated system. Yeah. So thank you again, Professor Huang. So let's go to our next speaker, Professor Sangmu Li from Seoul National University. The title of his talk is Wintertime Snow Depth and Sea Ice Thickness Records over Arctic Ocean from AMSR and AVHRR measurements.
Can you see my screen?
Yeah, very well. Thanks.
Thank you for the nice introduction and thank you for your invitation. Hello everyone, I am Sang Mori from Seoul National University. I am very glad to present my works regarding the wintertime snow depths and sea ice thickness records of our Arctic Ocean from AMSR and AVHRR instruments. So this work is done by collaborating with colleague below listed, and I especially thank Dr. Ho-Yeon Shi who led this research. I'm going to start with a brief background and the associated scientific questions. As we know, Arctic sea ice and snow are considered as important factor for understanding Arctic surface energy budget, which is closely linked to the ice albedo feedback. There is an important phenomenon that is referred to as Arctic amplification, which states that lighting speed of the Arctic surface temperature is twice as faster than global surface temperature trends. This is closely related to the reduction in sea ice area. Fortunately, sea ice area has been continuously and successfully monitored from satellite passive microwave observations. However, Arctic Basin scale sea ice thickness, which is also important to diagnose the Arctic climate change, is hard to observe from satellite. We know that there are several available snow depths and sea ice thickness data set. The first is the field measured snow depths and the sea ice thickness. And another is the automated buoy measured snow depths and ice thickness. And the last one is the airborne radar or LiDAR measured snow depths and ice thickness data set. This kind of data set are quite accurate, but there is some limitation to cover Arctic Basin scale sea ice system. So there are several satellite programs to overcome this problem. One of them is the NASA's ISAT and ISAT-2 program, which has the LiDAR altimeter instrument which measures distance between sea surface and the snow surface, which is called to the total freeboard. And the other mission is the ESA's CRASAT-2 mission, which has a LiDAR altimeter. The LiDAR altimeter can measure the distance between sea surface and the snow ice interface. It is called to ice freeboard. This freeboard information is quite accuracy, but in order to convert this freeboard information into sea ice thickness, we have to have a priori information of snow depths. However, snow depth data is quite difficult to obtain over whole Arctic because of harmful and the severe weather condition over the Arctic area. So this snow depth data rely on some climatological data, which is generated using data which were measured during 1954 to 1999 by Soviet Union scientists. However, we know that snowfall has great interannual and the decade variability, so they should be a potential error to convert freeboard information into sea ice thickness. Due to this snow quality problem, snow depth quality problem, there is an inconsistency between two altimeters as shown here, which is definitely due to snow depth uncertainty. So now we can bring two important questions. The first is that how we can construct the Arctic Bayesian scale, long-term and consistent snow depths and sea ice thickness records from satellite observations. And if we have such kind of record, then we can bring another question, which is how Arctic snow depths and sea ice thickness are currently changed under global climate change era. In order to answer this question, we tried to make an algorithm for estimating snow depth and sea ice thickness simultaneously based on satellite passive microwave and IR products. Before talking about the algorithm itself, I would like to briefly tell you about the data set, three different data sets we used. The first is the snow surface temperature, which is based on the AVHRR measurements, and the algorithm is developed by Danish Meteorological Institute. And our science team recently made an algorithm for estimating scattering optical depth and the snow ice interface temperature using AMSR-E and AMSR-2 measurements. AMSR-E and AMSR-2 are the conically scanning microwave radiometer. So using those three different geophysical parameters of the sea parameters, we estimated snow depths and ice thickness simultaneously. Let me briefly talk about the hydrostatic balance equation. We know that sea ice system is under a hydrostatic balance, which states that weight of snow and ice is balanced to the buoyant force. If we prescribe typical values of densities of snow and ice and water, we can solve the hydrostatic balance equation when the two additional parameters are given. The first parameter is alpha, which is the ratio of snow depths and ice thickness. And the other is total freeboard. Total freeboard is the distance between sea surface and the snow top. In other words, if we have information of the ratio alpha and total freeboard, we can solve hydrostatic balance equation for estimating snow depths and ice thickness simultaneously. So the key points for estimating snow depths and ice thickness simultaneously is to estimate total freeboard and snow ice thickness ratio. First, I would like to how to total freeboard from satellite measurements. Actually, we just use ISET and ISET2 measured total freeboard instead of use of the AMSR-E measurements. However, there is some disadvantage using ISET and ISET2 measured total freeboard. There are two reasons. One is the total freeboard from satellite LiDAR observations are limited for a certain time and space. And there are 11-year time gap between ISET and ISET2. So we cannot make a consistent climate record using ISET and ISET2. So we tried to estimate total freeboard from the AMSR-E and AMSR-2. Recently, LiDAR 2018 estimated scattering optical depth due to snow and freeboard scattering. We know that scattering optical depth is physically related to the physical length or physical depth. So this study attempts to relate total freeboard to scattering optical depth. ISET and ISET2 total freeboard were used for training data sets, and we make a fit equation by relating those two kind of parameters, which are the ISET measured total freeboard and AMSR measured scattering optical depth. The left bottom figure shows SOD, scattering optical depth, versus ISET and ISET2 based total freeboard. We can clearly see that there is a strong linear relationship between those two parameters. So we generated the regression equation. And then it is applied for whole Arctic. And we validated the AMSR estimated total freeboard against OIB-based total freeboard. OIB indicates that operational ice bridge, which is airborne mission for measuring snow and the ice thickness and other sea ice parameters. So it is considered as quite good data for snow depths and total freeboard. This right figure shows airborne measured total freeboard versus AMSR estimated total freeboard. We can see that there is good agreement between AMSR and OIB measured total freeboard with small bias and RMSE. So we decided to use AMSR based total freeboard for estimating sea ice thickness and snow depths. And the second parameter we need for estimating snow depth and sea ice thickness is snow ice thickness ratio. In order to estimate the ratio alpha from satellite observation, we assume that time averaged temperature profile is nearly linear during winter, and conductive heat flux is continuous at the snow ice interface. These two assumptions are quite reasonable because there is no sunlight over the Arctic Ocean during boreal winter time. So we can write down the thermal heat transfer equation as like this, and taking a ratio of snow depths and ice thickness, we relate alpha directly function of the ratio of thermal conductivity K at the snow and ice layers, and also function of temperature gradient at the snow layer and the ice layer. However, it is difficult to obtain the Arctic Basin scale information of thermal conductivity of snow and ice. So we decided to relate alpha with the ratio of temperature gradient. In order to do that, we collected buoy data set provided by AWI, Alfred Wegener Institute. The total 18 buoys were used, and we made a monthly average temperature profile. And in doing so, we also collected snow depths and the ice thickness data set from buoy measurements to relate those two parameters. This figure shows the buoy measured alpha versus buoy measured temperature gradient ratio. It is interestingly noted that there is a strong linear relationship between two parameters. So we generate a fitting equation says like this. In this slide, I would like to present the algorithm itself. As I mentioned before, there is an AVHRR-based snow surface temperature dataset and AMSR-based snow ice interface temperature dataset. In addition, the ice bottom temperature is constant, which is minus 1.8. This is not Kelvin, Celsius degree. So we can calculate temperature gradient at the snow and ice layers. So ARPA can be obtained from satellite-based temperature information using the generated fit equation. Also, I mentioned before, AMSR E and 2 provide scattering optical depth, which can closely related to the total freeboard. So we made a fit equation. So we also have total freeboard from satellite observation. From now, we have ARPA and FT from AVHRR and AMSR measurement. So using hydrostatic balance equation with a prescribed typical value of snow, ice, and water densities, we can estimate snow depths and sea ice thickness simultaneously. This slide shows a result for snow depth estimation on the Arctic sea ice for January, February, March of 2003 to 2020 period. The left figure shows a validation result. X-axis is airborne measured snow depths. The y-axis is the estimated snow depths in this study. So we can see that one nice one-to-one correspondence between two parameters. And we also take a mean and trends of the constructed data set. We found that young sea ice area here, the snow depths on sea ice ranges from 6 to 16 centimeter, and the corresponding trend is slightly negative, but not significant. But it is noted that over old sea ice area here, snow depth is quite deeper than snow over the young sea ice, and there is a significant increasing trend up to plus 0.6 centimeter per year. This is quite huge. This is because of a recent storm visiting frequency has increasing trend. And also, we know that old sea ice disappeared and remaining area is occupied by young sea ice. So there is a significant decreasing trend of snow depths, which is because of the accumulation time difference between old and young sea ice. In addition, we made a new snow depth climatology. As I mentioned before, the previous climatology is based on the measurement during 1954 and 1997. So the new snow depth climatology gives us an opportunity to convert ice freeboard into the sea ice thickness more accurately within the satellite altimetry system. We can see that snow depth has been reduced significantly. For instance, over the Western Arctic, 62% reduction in snow depth is observed. This is quite huge. And there also, we also estimate that the detrended interannual variability of the Arctic snow depths, which is slightly increased compared to the old climatological report values. The next is the mean field of the Arctic sea ice thickness. The left top figure is the Arctic sea ice thickness distributions from the study, and other three plots are based on the model and the radar altimetry based sea ice thickness data set. We can see the spatial distributions are well corresponding to each other. So we can conclude that the suggested simultaneous algorithm for estimating snow depths and sea ice thickness works very well over the Arctic area. We also checked that the time series of mean sea ice thickness over Arctic Ocean. As we expected, the ore products shows mean sea ice thickness over the Arctic Ocean has decreased. However, it is interestingly noted that in recent year, ore products shows the sea ice thickness trends seems to be neutral. I don't know why, but I will analyze this kind of trend data set with respect to other geophysical parameters like AO index and other index parameters. And this is a summary. The introduced method uses the snow ice thickness ratio from ABHLR and AMSR, and to convert total freeboard FT from AMSR to snow depths and ice thickness simultaneously. And the sea ice thickness and snow depth records were constructed using the satellite measurements of ABHLR and AMSR measurements, which the data set we generated shows in a good agreement with other products and the in situ measurements. And future plan is we will conduct additional climate analysis to understand why recent sea ice thickness trend is neutral. Thank you for your attention. Thank you. Any questions?
Okay. Yeah, thank you, Professor Lee. So it's very impressive. Yeah. We have time for one question. No. So I wonder, when you compare like AVHR and AMSR, so is the like calibration, are there any problem with calibration, or will calibration affect the derived trend and comparison?
Yeah, AVHLR and AMSR both have calibration issues. So DMI Danish Institute, Meteorological Institute make a calibration coefficient for AVHLR deployed in different platform. So they solved such kind of problem themselves. And the AMSR E and AMSR 2 have shows large difference between their brightness temperature. I know AMSR was still operating, is still operating, but its rotational speed is much slower than before. But so they make a calibration coefficient. JAXA made the calibration coefficients and distributed the coefficient. So I just applied it.
Yeah. Okay. Okay. Thanks again. So
Thank you.
our our next speaker is Professor Hiroto Nagai from Waseda University, and he will be talking about findings and challenges of a star-based snow depth mapping for Japanese wet deep snow. Yeah, welcome, Hiroto.
Yeah, thank you for your introduction. My name is Hiroto Nagai, working for Waseda University. Thank you very much to having this international opportunity to talk about my topic. So my presentation is about snow depths in Japan. Okay, let's start. Can you see my presentation slide normally? No problem. Okay, then let me start it. So this is very cold, like this is a winter scenery in Japan, in Niigata Prefecture, my study site. So my study is based on these contributors, mainly from national institution and Japanese universities, including my students. And this study was supported by 3 of Japanese foundation. So I would appreciate this great support. So this is my brief introduction. I was working for JAXA, Japan Aerospace Exploration Agency, until 2018. And after that, my main job place was Boston University, and partially working for National Research Institute for Earth Science and Disaster Resilience, that is called NEED, Japanese National Institution. So my main work is such a in situ observation of Japanese snowpack, and my main tool is remote sensing, mainly SAR satellite. This is my brief introduction of the SAR satellite, synthetic aperture radar. So the signal of synthetic aperture radar reach to the snowpack. Then first this surface reflection occur, and after that volumetric scattering and ground scattering occurs. So there are 3 parts of scattering, and using this method, some of previous studies developed estimation of snow depths, mainly for inland dry area of the continent, like Asia or America. So, but this varies. Snow depth valley is very shallow, about 28 to 20, just below 20 centimeters. But Japanese snowpack is very deep and wet, so I want to develop such an optimized method for Japanese wet snow. And as a previous study, Dr. D presented that there are poor research about snow depth measurement, but the spatial resolution is very large, about in this case 25 kilometers, using AMSO satellite, AMSO sensor. In my site, I'm planning to use ALOS 4, Japanese brand new synthetic aperture radar before launch. So that is because the rocket has some trouble about the rocket engine. So the launch period is not yet coming. But it has higher resolution, higher spatial resolution of 3 meters. So this is very good to observe snow layer in Japanese very complicated, complex topography. So my task is to make high-resolution snow depth maps for Japan. I will talk about the social demand for snow mapping. This is a picture of Japanese paddy field. The place name is Uonuma. That is a very famous place for Japanese delicious high-grade rice production in Niigata Prefecture here. In the winter, there are deeper snow like this, and that reaches almost 3 meters in the mountain side and about 1 meter in the plain coast side. So this snow pack should be removed for the local living, and it takes 13.5 billion Japanese yen for annual snow removal operation every year. So that costs much on Japanese local governance financial issue. So the wet snow is very heavy, so we need much fuel and a lot of snow removal vehicles like this. So it costs seriously for Japanese society. So our idea would save this situation. That means satellite analysis reveals snow depth maps, and that is a very critical information for a reasonable snow removal operation. So that causes moderation of local financial cost. Then that will make a sustainable agriculture in a high quality for the local area in Japan. So this is my main motivation to make a surface snow depth map. So my story contains three topics. One is L-band, longer wavelengths SAR satellite, and second one is C-band SAR, and the third one is an experimental activity using corner reflector read in the snow. First one, L-band SAR satellite that has 23 centimeter wavelengths in the case of Japanese ALOS 2, Pulsar 2 sensor. We collected 2 seasons data. One is snowless data, and another one is snow-covered data. So these data are converted to a physical unit of decibel and make some smooth filter and comparing each other. Then after that we need calibration of this difference decibel difference. So we use a network snow in situ snow depth measurement network operated by Niigata University. So there are about 200 points in Niigata Prefecture like this. So we collected this in situ data and make a calibration using linear regression, and after that this backscatter amplitude difference would be converted to snow depth distribution. Using this method, only in situ observation, we have such a very coarse map of snow depth, and after our study, that will turn out to be this very high resolution image of snow depth. So this is corresponding to the local topography of mountainside or valley topography. So that is very reasonable figure. But we need a critical setting of parameter. The critical one is smoothing filter. So I mean, without smoothing filter, the scatter plot of between snow depth and the backscatter amplitude difference make very scattered figure like this. So the R is about 0.2. So this is not good for estimation. And after taking some smoothing filter, that turned out to be 0.7. So very reasonable relationship between in situ measured snow depth and the backscatter amplitude difference between a snowless season and the snow-covered season. So I mean, smooth filter is a fundamental parameter for correlation between snow depth and backscatter. One reason to take this filter is to remove speckle noise. This is a very fundamental noise on the SAR images like this. But taking some filter, that is very the speckle noise will be removed. But after that, the focus is not good, so we cannot distinguish. So with larger filter, we cannot distinguish the land cover and ground constructions. So we have to set the best optimized parameter of smooth filter. So we have some analysis, and after that we found that the best filter is about 300 meter radius for the filter processing. After larger than 300 meter, the correlation coefficient is very stable, so not so much changed. So the smaller size would be good. So we set 300 meter for this smooth filter. Then finally, we have optimized optimized map of snow depths here in Niigata Prefecture. So this is our achievement by Parasat 2 Parasat 2 sensor. But we have one remaining issue. So that is our calibration method is only based on the each date. So we need for each satellite data, we also need in situ measurement for the each date. So the after calibration, we have various gradient of this plot. So we cannot define one represented formula between in situ snow depth and the difference of backscatter amplitude. So this gradient is very different in each day. So this is one critical issue for this topic. Then next, let's move to the C-band SAR satellite. That has shorter wavelengths of 5.5 centimeter, and we use Sentinel-1 that is European satellites constellation. Using this satellite, deeper snow is not good for detection, but the shallow snow is very sensitive to be detected. For example, we drive a car along this green point, then we stop this area that is the boundary of snow removed road and not snow removing road. So there are much snow layer that that hampers us vehicle proceeding. Then after that, we check the Sentinel-1 data. Then we can easily divide snow removed area and the snow covered area. And Parasat 2 L-band SAR satellite, then we cannot distinguish with this shallow situation of just about 0 centimeter depth and 50 centimeter depth is too shallow to detected by a Parasat 2 L-band SAR satellite. So this figure shows that sensitive detection of snow-covered roads is possible by a C-band SAR satellite. And also Sentinel-1 distinguished a snowless situation and little snow year between 2019 to 2020, and heavy snow year in 2020 to 2021. And in detail, the SAR satellite distinguishes road without the snow cover here. This is a main road. And on the other hand, urban area is not good for snow detection, as well as a forest area. So more zooming up, paddy field is easy to detect snow cover, but forest areas are not good for snow detection. So this is our findings of the limitation of C-band SAR satellite. And after that, we have some experimental activity using corner reflectors set in Niigata. So corner reflector is constructed by 3 panels, and that reflect very efficiently the SAR signals on the ground. Then we set very strong structure by steel and stainless steel to make 1 meter cubic panels like this, and that has a slit that has 2 slits for water removal, and that is set like this. In Niigata Prefecture, 2 points of this is lower elevation site, and this is higher elevation site named Need and Tashiro. Like this, we set the 2 corner reflectors for ascending orbit and descending orbit each other. And this Tashiro satellite, Tashiro sites, we have 2 corner reflector in 1 pixel. In 1 pixel size, and after that we have oppositely 2 corner reflectors, and this is tricky setting that this signal would be hampered by forest. So we wanted to check the effect of forest. Then we have interval camera on that CRs, and normally that is covered by snow over 1 meter. Very good accumulation here. Then this is backscatter amplitude time series since 2016 to 2020. And after CR construction, the reflection of VV polarization increased much up to 0 decibels. But VH polarization have not so much changing. Then after CR setting, that reflects strong signal in snowless station, but snow-covered station like this snow depth profile, then that is corresponding, but saturated in one in a level, like here about minus 17 decibel. In the mountainside, higher altitude area, Tashiro, this is a very rough surface originally. So the snow accumulation reflected smaller signal also in VV and VH polarization. And after CR setting, sorry, the VV polarization reflects a stronger signal about 5 decibels, and VH signals reflect about minus 14 decibel, and that is a good correlation between snow depths and the amplitude decreasing. So these activities, these experiments give us one idea that the very strong reflecting pixel is decreasing to no larger than minus 10 decibel when snow covered season. So we set this level about the threshold to detect bright points for solar reflection. Then next, this is the final step of our study. In the Google Earth engine, Sentinel-1 satellite can be analyzed. So we set this minus 10 decibel as a threshold for bright pixels. And we compared snowless season and the snow-covered season. Then here there is a series of mean snow mean difference. This is this blue dots caused by snow covering. So we can easily compare how much snow cover was caused in this in each season. So 2016 to 2017, there are much snow in most area of eastern Japan, but here very small amount of snow cover was detected from 2019 to 2021. And this is more short period analysis, monthly mean figure for 2020. So looking at the Niigata Prefecture, the upper panel, 2020, is a very small snow amount, and 2021 in the lower panels that has very heavy snow season. So comparing upper panels and lower panels, 2021 has we had much snow in Niigata Prefecture here, and after that we have in March we have much snow detection in Hokkaido area. So that is maybe possibly because the Hokkaido's snow is very dry, and as the previous presentation told, the dry and a small amount of snow signal penetrates these shallow and dry snow. But after that, in the melting season, such a dry snow turn out to be a very water saturated condition, then the signal will be increased. So this is my summary. So I am and my team is challenging to make high resolution and high accurate snow depth estimation by search. And originally, Japanese wet snow have some difficulties, but there are many solutions, many purpose to use this map for example, melting water management or transportation resiliency, and also for winter sports resiliency. So I'm trying to continue and upgrade this study for several years in the future. Okay, that concludes my talk. Thank you very much.
Okay, thank you very much, Professor Hiroto Nagai. So we have one question here. So
this question is about volcanic ash mixture. Unfortunately, we didn't have such a big eruption in our. Oh, can you hear my voice correctly?
Can hear you.
Yeah, we can hear you.
Oh, my monitor is stopping, so please be patient for a moment. Okay, I will switch off my monitor to keep the signal. Okay, can you hear my voice?
Yeah, we can hear you.
Yeah, okay. We okay, then I will answer this question. So which ones? We unfortunately we didn't have such a significant volcanic eruption for our study season. So so I cannot say something about the volcanic ash mixture. But originally, volcanic ash is very dry, so in my imagination, volcanic ash will not so affect this study. And just yeah. Yeah, I didn't check, but in my impression, such a very small amount of particle do not will not affect our observation. This is answer to Dr. Lee. Is that okay for you?
Yeah, thank you very much. It was
Okay.
a nice talk. Thank you.
And after that, a question from Dr. Shu. Which one has more impact on agriculture, wet or dry snow? So this question means agriculture, wet or dry snow. So yeah, in this context, wet or dry snow both are okay for agriculture. For agricultural operation, more important thing is very extreme heavy snowfall. So Japanese snowfall is changing to very short term, but short time period, but larger amount of snow. And the total amount of snowfall is getting smaller and smaller in these years, and corresponding to climate change. So that is more important for the Japanese agriculture. The total amount of snowfall is getting smaller and smaller, but sometimes we have very extreme snowfall in short term. Yeah, that is a very critical issue for Japanese society. Is that okay for you? Okay, thank you very much for your question.
Yeah, okay. Thank you again. So I guess we'll have about 5 minutes break here. And the next session will be hosted by our co-chair Yunju Li. Okay, so see you in 5 minutes.
Yeah, sounds good. Yeah, hello. Hello. I hope you are hearing me.
Yes, we can hear
Yes,
you.
we can hear you.
Yeah, great. So I think 5 minutes is quite short. It's already finished. So let's just start next part, second part of the event today. So yeah, our next speaker is Rubin Jiang, and they're going to talk about high resolution detection of lightning and thunderstorms in Shandong triggering lightning experiment. Please, yeah, share your screen and feel free to
Okay.
start.
Okay, thank you. It is my great honor to have this opportunity to present our high resolution detection of lightning and shadow triggering lightning experiment. And I am Rubin Jiang from the Institute of Atmospheric Physics, Chinese Academy of Science. Okay. And as we know, during the life cycle of a thunderstorm, the complicated dynamical and macrophysical process lead to charge separation of the hydrometers and eventually lead to the electrification of the cloud. The occurrence of lightning is dependent on the charge structure of the cloud, which is closely related to the environmental conditions, such as the water content, the temperature, and the hydrometers at different heights. So the relationship is complicated, and the detection of both the lightning and thunderstorm are the basis of a good understanding. The occurrence of natural lightning is random and propagate in a very fast speed. So it is hard to conduct direct and closed detection. So to overcome this difficulty, the triggering lightning technique is developed by launching a special rocket traveling a conductive wire. The lightning is triggered. Here we can see the rocket ascend in the speed of about 200 meters per second, and at about 200 to 400 meters height, the lightning can be triggered. The triggered lightning is occurred in a given time and space, so we can conduct simultaneous comprehensive detection by different means of technique. So this photo shows the rocket launcher, and the control room is located at about 100 meters away from the rocket launcher. And in the center, there is a Faraday cage. The current sensor, that is the very small resistance with the several milliohms is located here, and to directly measure the discharge currents of the lightning. And here we can also see a tower, and this is for testing the protection technique of the lightning protection system. And we can test whether or not the system works and can protect the devices here. And the data also help us to improve the lightning protection technique. And at about 1 kilometer away from the launcher, optical and electromagnetic field sensors detections, and as well as the lightning radiation source locating system are equipped, including the commercial speed video cameras, which can take the images at a frame rate of up to several tens or even hundreds of kilo frames per second. And also the by-time resolved optical devices designed by our group have the sampling rate of 100 million seconds per samples per second, and A radiation source mapping system can also depict the lightning developments. Here shows an example of the observation. We capture the detailed propagation of the lightning channel formation and extension at different stages, such as the ABC here, and simultaneously measured discharge currents, the electric field, and the magnetic field are also detected here. The key point here I would like to share with you is the identification of the stepwise propagation of the so-called positive channel. We call it the positive leader here, and we identify the residue chrome residue structure during the leader pulsing stage. And the persistent effort in triggering lightning have helped us to get lots of new insight into lightning physics. Since the time is limited, I will not expand it. Next, I would like to introduce a task we have made efforts this year, that is the field sounding inside the thundercloud by balloon. Definitely, it is important to help us to understand the charge distribution within the thundercloud and help us to clarify the electrification mechanism of the thunderstorm, and also provide us information to reveal the influence of charge structure on the lightning occurrence. Here shows the sketch of the sounding system, including the balloon and the radio sound and the electric field meter with two metal spheres. The radio sounds record the time, the position, the temperature, and the relative humidity. The electric field meter measures the 3D electric field by rotating vertically and horizontally. We also developed a ground receiving system which record and display the signals in real time. Here shows some pictures of the experiments. To conduct this kind of observation is not an easy job. We have to overcome the difficulty of the heavy rain, the wind, and the threatening of the lightning. Nevertheless, we made it. I would like to share with you an interesting case with the stratiform region being well detected. The thunderstorm developed quickly but moved slowly, and the sounding experiment conducted when it is close to its dissipating stage. And at the time, the ground measured electric field was not very strong at about 2 kilowatts per meter, and real lightning was recorded. The vertical upward motion of the balloon was at the speed of 2 to 5 meters per second, and involves rising, falling, and then re-rising stage at about 4 meters height. And the vertical lapse of the rate of the temperature is minus 5.5 degree per kilometer, and at the 4.8 kilometers height, it is the 0 degree temperature. So we eventually figure out the electric field profile and the charge structure of the cloud. The electric field ranged from minus 56 kilowatt per meter to 55 kilowatts per meter, and we recognize the bi-charge region with the polarity alternated with height. That is the positive and the negative alternated to distributed vertically. And at the 0 degree level, the charge polarity was positive. And let us look into the interesting results during the rising, the falling, and then the re-rising stage. at about 3.3 to 4.4 kilometers height in the main active charge layer. We can see that they are mostly the same, but not mostly similar, but not exactly the same. Especially, we can see that during the rising stage, there is some more positive charge layer identified. So the charge structure of thundercloud is more complicated than expect, and it also tells us that the charge structure is very changing with time. So, okay, by figuring out the charge structure, the investigation of how the charge structure influence or produce lightning may need a very detailed depiction of the lightning formation. But the optical cameras are unable to reveal the in-cloud lightning developments because the obstruction of the cloud. So we developed VHF interferometer to locate the lightning radiation source. It is based on the 5 times of detection of lightning radiation signals, and the time differences. The time differences by different sensors provide information of angles of the incident wave. One station of the interferometer with 4 to 5 sensors is able to depict the 2D propagation of the lightning. And by intersecting the 2 station results, we are able to obtain the 3D location of lightning radiation sources. So here is the method, and I will not explain it in very specific. Next, I would like to show the mapping results. Here is one example of the inter-cloud lightning flash. As we can see, the very detailed trend of spreading is depicted, and we can find large horizontal components and the upper and the lower channels, mainly in 2 layers. This represents the 2 main charge layers, and there is a vertical channel breakdown connects these 2 layers. Here shows a hybrid inter-cloud CG lightning flash, that is a cloud-to-ground lightning flash preceded by a long-term inter-cloud discharge process. And the this CG flash initiated at about 4 kilometers height, and there were several upward branches at its initial stages, and the downward channel extension eventually struck to the ground with 2 ground terminations. And we overlap the lightning channel with the radar echo to explore the relationship. The discharge involved area are identified as the upper positive and the lower negative. So we also find that inter-cloud lightning initiate at relatively higher location near the positive charge region, while the cloud-to-ground lightning initiate at a relatively lower location near the negative charge region. And both lightning flashes started at the edge of the strong echo, but not within it, as we can see the figure. As we know that generate a cloud-to-ground lightning flash neutralize the cloud charge in a single polarity. It is really found a lightning flash to lower both positive and negative charge to the ground, which is called the bipolar lightning flash. So during the experiment, we triggered this kind of special lightning, and it involved 2 times of discharge polarity reversal from the negative to positive, and then change to negative again. So we try to analyze the physical mechanism based on the detailed data. The radar echo shows that the triggering set was located at a section region between the convective and the stratiform cloud regions. And the positive breakdown, the positive channel propagated into the stratiform region, then the negative channel breakdown developed towards the convective region. And a key point is that some reactivity channel links the charge regions with different polarities. And we eventually figure out the mechanism concept of both the bipolar lightning with several key points or several key conditions needed. The first is the positive and negative charge regions at similar heights. Then the cutoff the discharge and then the reactivation. The newly activated channel extend to the opposite charge region. And finally, the rebreakdown at a cutoff points open up the current flowing channel to the ground and eventually make the bipolar lightning. I would like to stop here. And finally, I would like to say that our experiment is an open platform. So we look forward to the cooperation with colleges who are interested in the lightning and thunderstorm research. Thank you.
Thank you very much for the interesting talk. So we have time. I think we can get 2-3 questions. So if you have any questions, you can use questions and the Q&A option, or you can also type in the chat box. While waiting for questions, may I ask you some naive questions? So I actually have 2 naive questions. So first question is that why do you use 970 nanometer instead of visible wavelength? And the second question is that so my first naive question is that why do you use 970 nanometer instead of visible wavelength? That one of the slide was showing that observation.
You mean,
sorry. So it's a 700 meter altitude.
It is not designed. It is depends on the it depends on the condition we make the observation. That is this is the room we put our equipment to make the observation. We cannot make the observation here because during the thunderstorm it will be rain, so we have to put here. No other places have the condition for us to put in the equipment, and the rocket launcher is here determined. So we can make other distance if the observation set is in other places for us to equip the detection. I mean, it can be other distances. It is not a designed distance. It is just distance and have the room for us to conduct the observation. So maybe if the run is located at a further distance, maybe 120, 200, 1,200 meters, it will be okay as well. It depends on where the run is.
Yeah, for my bad question, you gave me nice answer. Thank you so much. Is there any questions? So there is a question in the chat.
Could you please?
If you cannot read the chat box, I can read it for you, or it's one of our speakers. So perhaps you can unmute yourself and perhaps ask to read directly.
Yeah, I can ask the question. Maybe that's easier. I'm really interested in clouds and precipitation process. I'm actually a cloud physicist, but I present a different story today. So I just wonder, from your observation, if you can tell us a bit more about the important cloud dynamics and microphysical processes for triggering the lightning?
Well, I think we can detect the result. That is, the cloud are charged, but we do not, during the experiment, we do not directly figure out the dynamical and macrophysical features. We how to say, we look at the radar echo. So in the strong echo area, if we locate it within, such as here, within the strong echo, so we infer that the charge are the electrification here is down, and the charge structure is suitable for the triggering lightning experiments. And this is one condition we refer to. And the second is that we detect the ground electric field. Yeah, like this here, we set up a field meter, and it will provide us the real-time detection of the electric field. And when the electric field at the ground is high enough, and we think that it is good for us to launch the rocket, that means we measure the electric field here, and it may represent the electrification or the extent of the electrification of the thundercloud. So this is the two main factors we refer to launch the rocket.
Oh, okay, great, thank you. I think it will be fantastic in the future in your field work if there are opportunities to deploy some of those in situ probes in your balloon to measure some of the microphysics in cloud. That will be.
You mean this experiment? Yes, we. But it is very not easy to.
Yes,
it's hard.
I respect that.
And
yeah.
And also we would like to bring some optical means to see the hydrometers inside the cloud directly in a close range. It will be very good. But also it will make the experience more complicated and more hard to conduct.
You're right.
So,
yes, I respect all that, but very
we are also
valuable.
trying to make the sensor smaller and smaller, but it is also need time to realize it.
Great, thank you.
Yeah, thank you very much for interesting talk, and we have to move to the next talk probably.
Okay, thank you.
Yeah, thank you. So our next speaker is Ho Ma, and they're going to introduce about the atmospheric retrieval of exoplanets using transmission technique. Yep.
Okay, thanks, Ian. First, I would like to thank the organizer of this nice webinar, so I can have a chance to introduce some of my group's recent work. Today, I'm going to talk about the atmospheric retrieval of exoplanets using transmission technique. I'm Bo Ma from School of Physics and Astronomy at Sun Yat-sen University in China. First of all, I would like to show the plots of the exoplanet discovery history. Ever since the first exoplanet detected in 1995, and for today, there are nearly 6,000 exoplanets have been discovered. And most of them are discovered using the technique called the transiting technique. And so if the exoplanet and their host star and the observer on the Earth, if all of us are lying on the same plane, then for each period, we can see that the planet will travel on its own orbit and block part of the light from their host star. So if we keep monitoring the flux or the intensity of the star, we will see there will be a sharp drop in the intensity from the star. So if we can see this periodic drop occurring, and then we can infer that there is some planet, transiting planet in this system. And on the right, I show an animation for real observations. And when the planet travel in front of the star and block the light, we usually call this the primary transit. And after half a period, the planet will slowly hide behind their parent star. So the star will block light from the planet, and we usually call this the secondary transit. And from the observing of the primary transit, we can infer information from the planet's atmosphere in between the terminator between the day side of the planet and the night side of the planet. And from the secondary transit, we usually can infer the thermal emission from the planet. And here we only focus on the primary transit and the transmission observation. The first transiting planet discovered is in 2000 by Chapman et al. Its name is called HD 209458. This is the name of the star. And the B means it's the first exoplanet in this system. And by using photometry from the ground, they observed there is a 3.5 days period exoplanet in this system. And by calculating the flux ratio variation during the primary transit, they can calculate the size of the planet is similar to our Jupiter. And one of the most striking discovery for today is called the TRAPPIST-1. And there are 7 planets have been discovered in this system. Among them, 3 out of 7 may sit in this so-called habitable zone, which is mainly defined by the equilibrium temperature of the planet, which is suitable for the existence of liquid water. However, to say exactly whether these 3 planets are habitable, most of the astronomers believe we need to do remote sensing of their atmosphere to see whether their atmosphere shows some feature of life. And to answer these questions related to the atmosphere of exoplanets, we usually need to rely on 2 different kinds of techniques. One is called transmission spectroscopy. The other is called directly imaging. Here, we only focus on the transiting planets. So we will focus on the transmission spectroscopy technique. And for nowadays, most of the information from exoplanets' atmosphere are derived using transmission technique. So when the host is, when the planet, we have a planet here and the observer is here and their parent star is here. And when the planet travels in between their parent star and the observer on the Earth, the light from their host star will pass through the atmosphere of the planet. And in the atmosphere, they have a lot of molecular and maybe atomic species, and the scattering and absorption of those atoms and the molecules will alter the light from the host star. So by measuring the different planet size at different wavelengths, we can obtain the transmission, the so-called transmission spectrum. And from the once you have the transmission spectrum, then we can use the atmospheric retrieval technique to deduct the atmospheric structure information like chemical abundance, pressure, temperature, profile, etc. Those information from the spectrum. So how do we do atmospheric retrieval? The process is shown in this diagram. We first need to obtain the observation, the spectrum, usually from a ground-based or space-based telescope. Secondly, we need to have a parametric atmosphere model. And from this model, with input parameters like the pressure, temperature profile, and the chemical composition, we can calculate through radiative transfer, we can calculate the model spectrum. Then we compare the model spectrum and the observed spectrum using some parameter estimation method. We can derive the posterior distribution of the atmospheric parameters. Next, I will talk about the input of the atmospheric retrieval. The first input is the pressure temperature profile. Because the atmospheric spectrum is governed mainly by the pressure temperature profile and the chemical composition. Given a pressure temperature profile, we can obtain the pressure and the temperature as a function of radius of the planet. Then we can use to determine we can use the assumption of a hydrostatic equilibrium and ideal gas equation of state to determine the function of a P, T, and related to the radial distance. And the most used pressure temperature profile by astronomers are 6-parameter profile or 5-parameter profile reported by Seeger et al. And Grillit et al. In 2009 and 2010. And here is one plot of the pressure temperature file from our model. The second input is we need to tell the chemical composition. And given the parametric chemical composition and the volume mixing ratio of each component, each molecular component and atomic component, we can calculate the mean molecular weight and the total number density. And usually for the hydrogen-rich species, the parameter absorbers used are water, CO, methane, CO2, sodium, potassium. And the mixing ratios are typically assumed to be uniform in the atmosphere. And so far, the detection of water, methane, sodium, potassium et al. Have been reported by astronomers. And the third input is the opacity from cloud or haze or dust or aerosol. And the effect of clouds and haze on exoplanetary transmission spectra is spotted through the subdued spectral features of some of the prominent chemical species like water and sodium. And it is initially raised to solely explain some of the observations. And here is one of the plot showing the impact of by including a cloud in the atmospheric model. If there is no cloud, then the light from the parent star of the exoplanet will pass through the atmosphere of the planet. But if you include the cloud will block most of the light from their parent star, and this will make the absorption. This will weaken the absorption feature on your transmission spectrum. So if you spot a weakened absorption feature in your transmission spectrum, then you can infer there may be some cloud or haze existing in the atmosphere of exoplanets. After we have a atmospheric model, we can calculate the opacity structure of its atmosphere. Then we can use radiative transfer to calculate the emerging transmission spectrum from this planet. Here I just show one slide of the basic equation used in radiative transfer. Basically, when the light from the star passes through the atmosphere of the planet, it may gain some intensity or may lose some intensity due to absorption and scattering extinction of the molecular or atomic species in the atmosphere, which is described by this term. And using the radiative transfer, we can easily, if we know the opacity structure, then we can easily calculate the emerging transmission spectrum from the planet. I show the equation here. It basically is calculated using the opacity model, calculated when we know the pressure, temperature, profile, chemical composition, and the cloud structure in the atmosphere. Once we know the opacity, then we can simply do an integration to calculate the transmission spectrum, which is dependent on the wavelength. And after we calculating the model spectrum, then we need to compare the model spectrum and the observed spectrum using some parameter estimation scheme. And this is usually done using a Markov chain Monte Carlo algorithm or a nested sampling algorithm. And they are the most widely used Bayesian inference method in astronomy. And then in the end, here I show one of the retrieval example for HD 209458b, which is the first transiting planet discovered. On the left, the green dot here show observations, and the purple line here show as the best fitted model, the red line. And on the right is the inferred pressure temperature profile of this planet, its atmosphere, and some of the abundance derived from the retrieval process. And right now there are several popular tools used for the retrieval analysis. One is called Thorax. Tau means opacity. The other is called Nemesis and Camera. And most of them actually use Markov chain, Monte Carlo, or nested sampling. And all of them, including really scattering and collision-induced absorption in their opacity model. And tests have shown that they generally produce similar retrieval results. So you can pick each of them for your own analysis. I usually use the first one since This is from our collaborator. And the next, I will show some of the most important discoveries. The first one is the first time water has been reported in the exoplanet atmosphere from HD 29458. And the second and the third one are discovery of methane and the discovery of clouds on the exoplanet atmosphere. All of these observations are actually used the Hubble Space Telescope. Since more and more exoplanets have been observed using this technique, recently there have been several population study of hot Jupiters. They are Jupiter-sized exoplanets, but with very short orbital period. Trying to answer some important questions related to exoplanets, like what kind of planet tend to have thermal inversion in the atmosphere, which kind of planets tend to have a cloud or haze in the atmosphere, do all hot Jupiters show water absorption, and can the metal abundance tell us where the planets initially formed? Here I just show two of the population studies. One is by Singh et al. In 2016, in which you can clearly see the sodium and the potassium absorption feature. And most of them actually have also shown water feature. And the other is done this year by Chenjit et al. For 25 hot Jupiters. The data are all from Hubble Space Telescope. They have a lot of conclusions, but there are still a lot of open questions remaining. This means we need to obtain more observations. And next, I will talk about some of our group's recent work. This is a work we have submitted to Astronomical Journal. We are also using the Hubble Space Telescope as a spectral observation of a planetary system called IR98, in which there are three rocky planets called B, C, and D. Most of the atmospheric studies focused on hot Jupiters because they are easier targets to observe because their planets are much bigger. But nowadays there are very few studies of the atmosphere of rocky or Earth-like planets. This is because the size of the planet is really small. Thus, the atmosphere also tended to be very thin. So it's really hard to get useful observations, even with Hubble. And we are trying to see if we can actually detect some of their atmosphere. And we are using the Hubble wide field camera in the scanning mode. I try to get as much photons as we can. And the top left shows the image on the camera. And the bottom left shows the extracted spectra for the star and the planet. And then we need to remove the spectra of the star to get the spectra of the planet, which is a very difficult process. You need to be very precise. And on the top right, we show the model of the transiting light curve of the planet B here. And during
Uma,
yeah.
Excuse me, that the time is almost up. So is it
okay?
Please finish soon. Thank you.
Okay. Yeah. So here you can see the transiting light curve, which the fit is really well. Then we can extract the spectra from those three planets, the transmission spectra, from those three planets. And here we show their spectra and the best fitted atmospheric model. And for three of them, two we have not detected any atmospheric feature. But for the planet B, we have found the feature of HCN, and the abundance is nearly several percent, which cannot be explained by an equilibrium chemistry model we have run. So our conclusion is for the planet B, it possibly have a lot of hydrogen cyanide in a secondary atmosphere and a DC equilibrium chemistry model. Or if this scenario is wrong, then the second best explanation is we haven't detected any absorption in its atmosphere. And the future observation from James Webb can help resolve to tell us which of these scenario is correct. And here is our summary. And since my time is up, I will just stop here. Yeah, thanks.
Yeah, thank you very much, Obama, for the nice talk. And because of the time, I think we can perhaps use the break time for further questions. Actually, I also have one question, and I would like to ask you later. So let's move on to the next speaker's talk. So the next one will be given by Shiva Chenoli, and going to talk about the linking the variability of the Antarctic sea ice extent in the Indian Ocean sector to Indian summer monsoon rainfall.
Hi, can you see my screen?
Yes, but could you try presentation mode?
Yes, yeah, I'm okay.
Yeah, excellent.
Hello, everyone. Many thanks to the session chair for the introduction. As you heard from the chair, my name is Shiva Chenoli, and I'm a faculty member in the Geography Department, and I'm also a research associate at the National Antarctic Research Center. So for my talk today, I will highlight the key outcome from our research on the teleconnection between the Antarctic sea ice and the Indian summer monsoon. And also, I would like to take this opportunity to give a brief account of the action group I'm chairing, which is called the Tropical Antarctic Teleconnection, TATE. And this action group is under the Scientific Committee on Antarctic Research. So that will be after my talk on the sea ice extent and Indian summer monsoon rainfall. So let us look at the background of the study. Any statistically significant long-range linkages between the high latitude and low latitudes are usually referred to as teleconnection. And a teleconnection is important because understanding the atmospheric teleconnection can give you more insight into the interaction between polar region and tropical region, especially like how the polar region influences the Asian monsoon, etc. Right, and teleconnection studies also may be able to enhance the predictability of monsoon system and their strength. So this is the motivation of our study. So if you scan through the previous literature, you can see most of the earlier work on tropical Antarctic teleconnections was primarily looking at the ENSO-related teleconnection. That means how the ENSO is impacting on the various meteorological parameters over the different parts of Antarctic. And after that, there were a series of studies followed focusing on the teleconnection stemming from the Atlantic. And in recent years, more attention has been paid to the teleconnection between Antarctic, middle latitude, tropical climate variabilities, including that of Indian summer monsoon rainfall, or Asian monsoon rainfall, right? So there were many statistical studies involving Antarctic sea ice extent variability and its global connectivity, which clearly demonstrate the impact of polar ice on middle latitude and tropical latitude. And some of the recent studies also shown that the variability of summer monsoon rainfall in eastern China is closely related to the sea ice, Antarctic sea ice coverage. And there are studies by Prabhu et al. Reveal that the sea ice extent of the Western Pacific Ocean sector and Bellingshausen and Amundsen Sea also strongly related to the Asian summer monsoon rainfall variability. So as we all know, Antarctic sea ice extent is extremely important feature in the southern polar region. It is also known as an essential factor in the climate system. Its variability influences global systems regionally, remotely, including both physical as well as the biological system. So over Antarctic, there is a statistically significant increase in the sea ice extent, about 1.8% for a decade, and which is in contrast with the 4.4% of decrease in the sea ice extent in the Arctic. And each sectors of Antarctic sea ice extent experienced and displayed different variability in the time scales, and also it has different impacts. So over the past decade, the interaction between sea ice extent and the tropical climate has been studied extensively by various researchers. And in future, if the Antarctic sea ice loss occurs, and then it may lead to substantial, robust impact on the spatio-temporal distribution of monsoon rainfall. So here we plan to look at the linkages between the sea ice extent at the Indian Ocean sector, because the Indian Ocean sector experienced the second largest annual amount of increasing sea ice after the Weddell Sea, and the physical process that controls the seasonal sea ice growth or decay, as well as its interannual variability, is poorly understood. And there were less meteorological work that has been carried out compared to the other sectors. And also geographical position of Indian Ocean sector is in line with the Mascarene High and also the Indian region. So to see whether there is any relationship between the Antarctic sea ice extent and Indian summer monsoon rainfall, we first try to examine there is any statistical linkage between sea ice extent and Indian summer monsoon rainfall. So in order to investigate the impact of variability of sea ice extent and on the Indian summer monsoon rainfall, the correlation analysis between the sea ice extent at different sea ice sectors, including the Indian Ocean sectors, during different composite months as March, April, May, June, etc., with the Indian summer monsoon rainfall were examined first, and the time series of normalized the sea ice extent in the Indian Ocean sector and Indian summer monsoon rainfall over the peninsular region gave the highest correlation compared to the other region, as you can see in this table here. So in order to gain a further insight, spatial correlation between the sea ice extent and also Indian summer rainfall were also examined. And the results, as you can see in this figure, shows that there is a high positive correlation over the shaded region, over the peninsular India region, which is consistent with the correlation analysis. And overall, this positive results gave a general view that the variability of sea ice extent in the Indian Ocean sector has a significant impact on the Indian summer monsoon rainfall. And we also look at the, to look at the influence of sea ice extent, we also look at the correlation between sea ice extent and special correlation between the sea ice extent and mean sea level pressure. And the correlation between this analysis shows that it is highest over the southern Indian Ocean between 30 to 50 degree, and that is positive correlation. In contrast, there is negative correlation found over the Antarctic continent and some parts of Southeast Asia. So this positive correlation area coincides with the location of Mascarene High region. So then we categorize the years as high and low sea ice phase based on the standard deviation, and further examine the composite difference during high and low sea ice years. These are the composite difference of mean sea level pressure and 500 hectopascal geopotential height, and also 800 hectopascal wind anomalies, wind vectors, right? For the months, the composite months. And this composite anomaly clearly shows a positive anomaly between the latitude of 30 to 50 south, and a negative anomaly over the Antarctic region. So the positive value indicates the intensification of mean sea level pressure over the southern Indian Ocean region and Indian Ocean sector, and inclusive of the Mascarene High region. However, this Mascarene High region does not represent the entire the Mascarene High system. And in addition, the two phases associated with a longitudinal movement of Mascarene High, location of Mascarene High is shifted more eastward from its climatological position during the high sea ice phase. And similar pattern also appear in the 500 hectopascal geopotential height over the second figure here, indicating the barotropic nature or feature of this analysis, right? So the positive anomaly was observed over the southern Indian Ocean, with the negative anomaly observed over the Antarctic continent. And mean sea level pressure anomaly, as the mean sea level pressure anomaly over this southern Indian Ocean increases, you can see the wind anomaly at 800 hectopascal shows very strong anticyclonic anomaly. And the northern branch of strong anticyclonic wind anomaly produces a stronger westerly wind as it crosses the equator over this area, and which shows enhancement of Somali jet during the high sea ice phase years. So Mascarene High over the southern Indian Ocean and Somali jet are some of the major circulation system that controls the Indian summer monsoon. So to get a better understanding of the relationship, we carried out the EOF analysis for the sea ice extent during AMJ. The first three leading EOF mode of sea ice extent during AMJ are presented here from figure A to C. The first EOF mode explain around 40% of total variance, and the spatial pattern of EOF1 shows negative anomalies of sea ice extent over the entire Indian Ocean sector. The second EOF2 mode explain around 70% of the variance and has a positive anomaly over the West Indian Ocean sector and negative anomaly to the east. And the third EOF or EOF3 mode explain 8.4% of the total variance, and it is characterized by the spatial pattern of a positive anomaly at the center and negative anomaly over the edges. And here you can see the sea ice extent appears in the center, where more sea ice, the extent appear over the same center, whereas less loading effects is shown in the edges of the sector. So similarly, the first three loading of EOF modes of precipitation during the JJS are displayed in this slide. EOF1 account for 27% of the variation, EOF2 12%, and EOF3 10% respectively. And it is shown from the figure D to F. Right. So the spatial pattern of EOF1 illustrated a positive precipitation anomaly over the northern part of the peninsula India and extending towards the Bay of Bengal, and a negative anomaly over the other part of the area. In contrast, a negative rainfall seen over the southwest the peninsula region. For the spatial pattern, EOF2 shows a dominant feature of positive rainfall anomaly over the Indian region, Arabian Sea, and Bay of Bengal. In contrast to EOF2, EOF3 shows negative anomaly over the Indian region, and whereas a positive anomaly over the Bay of Bengal region. So we continued this analysis by correlating the principal component of EOF modes of sea ice extent and summer precipitation. And the result shows that PC1 of the sea ice extent has statistically significant negative correlation with the PC2 precipitation with a correlation coefficient around 0.5, and PC3 of the sea ice extent has a positive correlation with PC2 precipitation with a statistically significant correlation of 0.4. And both value indicates that the sea ice extent in the Indian Ocean sector during the AMJ significantly impacts the Indian summer monsoon rainfall. In fact, both these patterns have similarities. If you recall EOF1 pattern, it depicts negative sea ice anomalies in the Indian Ocean sector, while positive anomalies characterize the EOF3. So this suggests that the EOF time series is positive for EOF1 if the Indian Ocean sector mainly be characterized by the negative pattern, and EOF3, the Indian Ocean sector will mainly characterized by positive sea ice anomalies. And the temporal patterns of these EOFs are also different. If you look at this figure here, the EOF1 time series depicts a negative trend, whereas EOF3 time series do not show any trend. So this suggests that these two patterns could result from different process, but they have same or similar manifestation on the sea ice extent. So therefore, for an in-depth analysis of this relationship, we selected PC1 and PC3 of AMG sea ice extent to identify the high and low ice phases. So high and low ice phases are categorized based on the absolute normalized values of PC1 and PC3 of sea ice extent in the Indian Ocean sector. So the list of high and low sea ice phase areas for the principal component of AMJ is tabulated in the table. And by high and the low sea ice phase, we mean that the presence of positive and negative sea ice anomalies in the spatial pattern of EOF1 and EOF3. So these figures, they display a spatial regression of geopotential height anomaly at 200 hectopascal superimposed with the composite difference of the wave activity flux corresponding to the PC1 and PC3 time series of sea ice extent in the Indian Ocean sector. So you can see at 250 hectopascal, the contours of geopotential height anomaly exhibits a kind of tripod structure over the Indian Ocean for both principal components. The first figure illustrates the positive anomalies over the polar tropical region and negative anomalies over the middle latitude. So composite difference of wave activity fluxes seen propagating mostly southwards from the tropics towards the polar region in two paths, and one is from the Australia, south of Australia, and the other from the Western Indian Ocean, both propagated towards the middle latitude around 50 degrees south and continued the propagation towards the polar region. Furthermore, wave trains appears to diverge into the area of Mascarene High, and this can modify the low-level circulation over the region, enhancing the low-level convergence during the low ice phase of PC1. In contrast, opposite features, you can see the geopotential height anomaly in the this B figure. A negative anomaly appears over the Southern Ocean and tropics, positive anomaly over the middle latitude. The composite difference of wave activity flux featured northward propagating wave trains from polar region towards the middle latitude. It's originated from the Indian Ocean sector, one propagated towards the middle latitude along the center of Indian Ocean, particularly over the Mascarene region. So this is due to the fact that positive EOF1 is characterized by negative sea ice anomalies, and the positive phase of EOF3 is characterized by the positive sea ice anomalies. This in turn means that positive sea ice anomalies in both EOF result in the similar wave propagation, hence stronger easterlies emerging from the Mascarene High can be expected over the Indian Ocean, contributing to the Indian's cross-equatorial flow, and strong southwesterlies over the Indian region, which consequently there might be increased rainfall over the Indian region when the sea ice anomalies were positive in the Indian Ocean sector. So this figure represents the vertical profile of the composite difference of zonal wind average corresponding to the PC1, that is figure A, and the PC3, that is figure B. And here too, both composite represent the opposite phases, since EOF1 and EOF3 are more or less represent the opposite phases of sea ice anomalies in the Indian Ocean sector. Similar argument can be presented, that is, which is similar to those in the earlier figure. Variability of zonal wind anomalies in the upper troposphere is closely related to jet stream variability that influence the atmospheric circulation feature. Also, a concurrent variation of the polar jet and subtropical jet serves as the critical indication of the interaction between low and high latitude circulation system. So a figure here shows that maximum negative and positive anomalies of zonal wind average are located at the 50-degree south and 38-degree south at an altitude of 400 hectopascal and 250 hectopascal respectively. So the difference in the maximum anomaly indicates that—
Excuse me, Shiva, the time is almost up. Yeah, time is almost up. Yeah.
Yeah, so you can see the similar figure in the opposing type of figure during the high sea ice phase and low sea ice phase. The composite difference in the anomalies of 200 hectopascal also shows the similar variation. And we can see during the high sea ice phase, both Ferrel cell and polar cell is weak, and compared to that of the low sea ice phase is weak compared to that of high sea ice phase. We also look at the composite difference of precipitation anomalies, which shows the similar pattern for high sea ice phase. We can see this is the OLR pattern, which shows high sea ice phase. We can see high OLR, which means less convective activity, and the reverse is true for the high sea ice CIS phase, right? So similar patterns are observed in the precipitation, and this schematic diagram shows the mechanism of teleconnection, where we can see strengthening of polar cell and feral cell and more increased convective activity over the Indian region, and strengthening of Hartley cell, which contribute more rainfall during the high sea ice phase. So these are my conclusion. And as I mentioned, there is this tropical Antarctic teleconnection group, which I'm chairing, and we aim to promote the international collaboration. So this is under the Scientific Committee on Antarctic Research. So if anyone is interested, you can send an email that we are trying to expand this, and we are going to get the extension for next 4 years. We usually arrange workshops, etc., and we also provide some kind of financial support for the early career, participants. So that's all from me. So this brings to the end of my presentation. Thank you very much.
Yeah, thank you so much, Shiva, for the nice talk. And because of the time, actually, we should combine the Q&A and the break time. So I would like to propose 5 minutes break from now. So here the Korean time is 4:37 p.m. So let's gather again. Let's resume the next session in 5 minutes. And Faye?
Okay.
Are you there? Yeah, thank you. So next chair will be Faye Chang. So Faye, just want to make sure that you heard what I said. Hello, Faye.
We didn't turn on your voice, Faye.
Yeah, okay. Okay, I heard that. Let's start 5 minutes later.
Yep, yeah.
Okay.
So in the meantime, perhaps we can use the break time for the questions, actually. So wait a second, let me just set some timer. So I think this question was towards Boma. In the chat, Joe Lee asked you about the question. Perhaps you can read the chat box too. So can you explain why you can use JWST observation to judge which scenario is correct?
Oh, okay, yeah. Yeah, I saw I saw this question. I think using JWST, it has the coverage of the middle infrared, and using only Hubble Space Telescope, the spectral coverage is only right now. They can cover only to 1.6 micron, but with JWST, they can extend the coverage to like 20 micron. So between 1.6 and 20 micron, there are several prominent absorption feature of hydrogen cyanide. So if we can obtain an observation from JWST and see the absorption feature coincide with the hydrogen cyanide, we can confirm there are actually a lot HCN in the atmosphere of R98B. Yeah, I think that's my answer. Yeah, thanks.
Using the chance, I want to ask you also another question. So I'm studying about Venus atmosphere, and the cloud is quite a difficult target to interpret exoplanet data. That's I know very well. And my question is that one of your slides was showing that to fit the observation spectra, you suggested to raise the cloud to fit to make better fit to the observations. And I'm just curious that because raising the cloud altitude or thinning the atmospheric density would have a similar tend a similar response? And is there some clue or reason that you prefer to raise the cloud?
Okay. I think your question is there are maybe some degeneracy between, I mean, to explain your observation, there may be several models or several scenarios you can use to explain the observation. And your question is why some of the, for explanation of some of the observation, we prefer to use the cloud. I think the result is probably from because we have a multi-band observation and from optical to near infrared. I think you use only use the cloud, you can explain the scattering feature in the optical band and the subdued, to explain the subdued absorption feature in the near IR. I think that's probably the explanation. Yeah.
Yeah, I know it's very difficult to distinguish, but yeah, thanks a lot for your answer.
Thank you. That's a very good question. Yeah.
And though I see there is also a question from Ihuang to Shiva, so please feel free to talk to each other directly.
Yeah, sorry for jumping in again. Actually, I think it's a very interesting talk that Shiva was giving. I just wonder, because we know that IOD has an influence on the Indian summer monsoon rainfall, whereas we also know IOD is not independent of ENSO, but ENSO has a strong control on the sea ice extent through teleconnection as well. So I wonder whether the relationship you show between Indian summer monsoon rainfall and the sea ice extent is actually fundamentally controlled by the variability of those large-scale modes.
Yeah, as you mentioned in your talk, there might be several interaction between the modes, right? But for the ENSO, we try to eliminate the ENSO impact using the partial regression, and we got the same kind of relationship, but we haven't tried about IOD. So this is kind of I can say it's kind of part of a iceberg, maybe, this relationship. Yeah, there might be several other complicated interaction that is going on. Yeah.
All right, thank you.
Faye, are you there?
Yeah, if no questions, let's start our last session today. We have two presentations in this session. One is about Tibetan plateau climate. The other is about wind and solar power. First, let's invite Professor He Bian give his talk about quantification of seasonal and interannual variations of the Tibetan plateau surface thermodynamic forcing based on the potential vorticity. Welcome, Professor He Bian.
Thanks, Chairman. I will share my screen first, and please wait a second. Yeah, it's my pleasure to attend this meeting, and I would like to introduce some studies about the Tibetan plateau climate dynamics about Tibetan plateau in my talk. Today, I would like to introduce our work in the following parts. Firstly, I'd like to show a movie about this great topography. So the Tibetan plateau located in the center of the Eurasia continent, and causes the altitude. It covers snow almost all the year, especially in the western part, and in the south part, because it's very steep. So it's the boundary of the monsoon regions. So on the south, you can see that many plants and crops. So it's because of the raining, and in the north part, is quite dry. So from the climate dynamics, the forcing of Tibetan Plateau can divide into two aspects. The first is dynamical forcing, and the second is thermodynamic forcing. For the dynamic forcing of the Tibetan Plateau, and it can be easily understand, there are many two effects. The first is it can block in the airflows, just like a stone in the water. The second, it can force some kinds of atmospheric waves, both waves on downstream and also in the vertical directions. And the thermodynamic forcing of Tibetan Plateau was proposed in 1957 by Professor Ye and Professor Flown in Germany. And they use spatial datasets and found the climate pattern in winter and summer are basically different between these two seasons. In summertime, it almost appears cyclonic circulation in the lower troposphere. So they assume that the Tibetan Plateau is a heating source in summertime. And with the studies in the past decades, more and more observations can be get, and this is from the analysis data from climate mean from 1979 to 2010. So you can see this is the climate mean pattern of zonal deviations for winter and summer. We can see that a dipole pattern appears in winter season, so it will cause anticyclone on the north of the Tibetan Plateau, and it will cause a cold climate in the North China, and it will, on the south it will cause a cyclonic anomaly. So on the southeast edge of the Tibetan Plateau, it will easily to cause rainfalls in spring seasons. And in summer, it appears almost anticyclone circulation anomaly. So it appears quite connect with Asia summer monsoons precipitation and circulations. And the next I will introduce some theoretical studies on the Tibetan Plateau dynamics, because the Tibetan Plateau forcing is closely connected with monsoon precipitation. So in 26, Yanani and Wu calculated the atmospheric heating source and whatever source that is Q1 and Q2, and they found they have a close connections, almost similar patterns with precipitation, with the large diabatic heating on the source of the Tibetan Plateau, and also with the largest water vapor source. So the liquid the strong monsoon convections are closely connected with Tibetan Plateau thermodynamic forcings, and they calculate the diabatic heating in different terms. For example, the red line is the sensible heating, and the green line is the latent heating, and the blue line is the radiation cooling, and the blue curve is the total heating. So we can see the annual cycle of the total heating is increasing over Tibetan Plateau and reach the maximum in JJA. But the sensible heating on the near surface, it reached the maximum mainly in spring and will decrease in JJA. But the latent heating increase rapidly. So there's a transition between the sensible heating and the latent heating over the Tibetan Plateau. In 1997, Professor Wu proposed a theoretical model that is called sensible heating driven atom, because the surface of Tibetan Plateau is heated by the solar radiations, so it will cause a low-level isentropic surface to bend into the Tibetan Plateau, and it will cause a low-level unstable, and it will more easily to trigger the convections, local convections, and vertical motions that drive the South Asia monsoon. So the heating on the slope is very important. If we only consider heating on the top of the Tibetan Plateau, it will only cause a quite weak of the vertical motions because a large amount of the water pattern is on the low level of the troposphere. They did the experiment based on atmospheric model in aquaponic water experiment. So in this experiment, they separate the surface sensible heating in different experiments. If they only consider the slope of the heatings, it will cause quite strong vertical motions, just like the control experiment. But if they only consider the sensible heating on the top of the quantum paddle, it will cause quite limited vertical motions, which suggested in the slope heating is important in the climate simulations. And there are also some uncertainties in the modeling simulations and climate observations between the Tibetan plate forcing and the Asian summer monsoons. This is a study of Mona in 2013. So they found the correlations between the Tibetan surface. They use MSE as the index of the heating, and the relationship with the Indian monsoon precipitation. This is correlations. They found the correlations only good in before and after the strong monsoon period. While during the GDA, the correlations are very, very low and it's not significant. In 2010, Bose and Kong studies, they use the HCM with also a 20 timers resolutions. They do such kind of experiment. This is a control experiment. They reproduce the monsoon patterns, and if all of the topography is removed, the monsoons only exist in ocean regions. But if we prescribe part of the Tibetan plateau, the south part, so it will reproduce quite similar precipitation pattern as the monsoon precipitation pattern in control one. And they tested the albedos in the top of the Tibetan plateau. The difference are very limited. Thus, they inferred the dynamical effects, not the heating effects is important. However, in their studies, slope heating is also considered in their experiment. So we reproduced their experiments, and we additionally tested if the Himalaya surface heating is removed, how summer monsoon will appear. And it's clear that if we without the surface heating on the south slope, the airflows can only cross the mountains and cannot climb up because there are no strong elevated forces force the air to uplift it. So we tested the different mountains, for example, the Iranian plateau and the Tibetan plateau, and they together, and we tested their dynamical and thermodynamical forcings, and the results suggested that the thermal surface heating effect of their combined effect is the most important for the establishment of the Asia summer monsoon, especially in the central and the middle of the Asia continent. And this is actually the thermal forcing is the most important. And this is studies, recent studies from Costa and Huber. They tested with 25 kilometers global model. So they tested different topographies in the experiment, and they found that if they only consider the Himalaya, it also still the change of the surface entropy, it will decrease. However, when it's very if it's very high, have a theta E in the local rest of the Indian, but the precipitation is not strong. So the local therapy maximum is not monsoon driven force, but the precipitation pattern is quite sensitive to the location and the shape of the topographies. So the monsoon response will be sensitive to the model itself and also the experiment design. And so we would like to know how to competitively estimate the surface thermodynamic forcing of the TP in the observation and the numerical experiments. So under the national velocity perspective, this is actually raised firstly by Hoskins in 1985. So the change of the potential velocity can attribute to the change of the W dating and also the frictions. So it's a nature of in nature, this is the galvanized authentic surface. It in nature it across the Tibetan plateau, and it is we can see that the Tibetan plateau is a forcing of the generation of the potential vorticity. It's a kind of we can see by calculation of the change of the potential vorticity, we can estimate the surface thermodynamic forcings. So this is the expressions of the PV in a three-dimensional directions, and we simplified it in the theta terrain followed coordinate with this vertical term. So this is the final form as we calculate in the surface. It's affected by the PS, and this is topography effects and also the dynamical effects and the thermal effects. Compared with often we use the sensible heating flux, it's considered the dynamic effects and the orography effects. So it will be more useful than the sensible heating as we used before. So this is the SPV distributions in JJ and DJF. This is the total term. We can see that a total SPV shows a very strong in Tibetan plateau, and also it's reversed in DJF seasons, which suggested in summer Tibetan plateau is a heating source and in winter is a cooling source. So this is a thermal term. We can see the thermal term is very similar as the total term. So the thermal term is a dominant term, while the dynamic term mainly shows is dominated by F and shows the lunar wind patterns, especially in the ocean regions, while the orography effects almost amplify twice of the total PV. So this is annual cycle. Can see we would like to show the relationship between the SPV and with the evolution of the Asia summer motion. This is a precipitation annual cycle between this latitude. We can see that the precipitation becomes stronger from spring regions and reaches maximum during JJ. If we use the sensible heating flux, we can see that the sensible heating flux will be decreased during this season. But we can see when we use the SPV, it has a good correlations with the evolutions of the summer precipitations. And we use the SPV as an index to calculate the sum of the SPV in this area, and we make an index. We can see that the index of the TP-SV PVI mainly shows interannual variations and increase in between before 20th century and decrease after 20th century. And we would like to do the cumulative analysis on the precipitations. So we accommodate the SPV with a high index and a low index with the differences. So accommodate SPV shows strong, mainly on the Tibetan plateau, and the precipitation mainly shows an increase. A dipole pattern, a meridional dipole pattern is shown here, and many increase on the South China and the West Pacific, and also South Tibetan plateau with tectonic alarming over the Eurasia continent. The linear regressions between this index and the precipitations also with regression with RC of 0.4. So it's quite good correlations, and the observation analysis is quite close with our numerical simulations before. So it means that we can use this index as a diagnostic for the model responses in future. And we also check the international interannual relationship between the SPV and the East Asia monsoons, and it also shows that it has close relationships. The correlation is very high with the triple pattern of the precipitation on the downstream. If you are interested, you can look into this paper in future. And this is the summary. I will not repeat. The point is that the SPV is better than the surface sample heating as a good index to representative of the Tibetan plateau thermal forcings, and it can be served as a metric for model evaluation and climate dynamics in future. And if you are interested, you can look into these references. Okay, I will stop here. Thanks for your attention.
Okay, thank you, Professor He Bian. Thank you for your excellent presentation. Are there any questions? Actually, I have one question. In your presentation, you show some results from the numeric simulations with and without Tibetan plateau heating. And from my side, I'm interested in, are there any interactions between the Tibetan plateau heating and the westerly jet?
Yeah, it's good questions. I think we have it really have some interactions, and also the most important thing is that the Tibetan plateau can affect the low level. It can trigger, for example, the monsoon precipitation, and it will cause a latent heating release in the upper levels, and this will trigger Rossby waves in the upper level and will propagate in the westerly jet. Actually, in our previous studies, we found the heating related, the latent heating related with TP forcings in East Asia will cause Rossby wave propagation on the west, relatively on the west side, and will cause downward motions on the west of the Tibetan plateau and will enhance dry climate in the IAMAS plateau and the surrounding regions. So on the contrary, we also have some studies. We found the NAO, the variations of NAO on interlinear scales. So the waves in Atlantic oceans can propagate along the westerly jet and can influence the surface SPV over the Tibetan plateau. So they really have interactions. Thank you.
Okay, thank you. Are there any questions? If no questions, let's move on to the next presentation. Thank you, Professor He Bian again. And let's move on to, yeah, thank you. Let's move on to the next presentation from Professor Wang Yang. His talk is potential contributions of wind and solar power to China carbon neutrality. Welcome, Professor Wang Yang. Thank you.
Okay. Thank you, Professor Zheng. Can you hear my screen?
Yeah. Yes.
Okay. Thank you for your invitation. And I'm Wang Yang from National Climate Center of China Meteorological Administration. Today, I want to talk about the potential contribution of wind and solar power to China's carbon neutrality. And as we know that in September 2020, China announced dual climate goals of peaking emission by 2030 and achieving carbon neutrality by 2060. And meeting both goals will require China to decarbonize its energy system. In 2020, CO2 emission from energy consumption accounted for 87% of China's total emissions. In the same year, energy sourced from non-fossil fuels accounted just for 59% of total energy consumption. According to IRENA, from 2010 to 2020, the global average, weighted average levelized cost of electricity for solar PV, onshore wind, and offshore wind fell by 85%, 56%, and 48% respectively. But on one hand, wind and solar PV power generation are intermittent and volatile. A high proportion of renewable energy will bring serious challenges to the safe and stable operation of the power grid. But on the other hand, wind energy and solar energy resources are complementary in time and space. Connecting wind farms and solar PV power plants in large areas can effectively smooth the volatility of wind power and solar PV. Optimizing the combination of wind and solar PV stations helps to improve the stability of their generation. And we also did some research about the spatial and temporal complementary of wind and solar power generation in China. And the results shows that in a wind dominated renewable energy system, expanding the spatial extent can significantly improve the stability of a power system. However, for solar PV dominated renewable energy system, this effect is not very significant. And we also found that only when the wind and solar PV maintain a reasonable ratio can their power generation be the most stable. So that's the background. Now we move to the scientific question. In this study, we want to answer two questions. The first one is whether the wind and solar PV power potential in China can enough meet carbon neutrality targets. And the second one is how to optimize the layout of wind and solar energy development in China and the scenario of a high proportion of renewable energy. Next is a research method. In this study, we only integrate wind and solar power into the supply side of our power system, and for the five reasons. The first is we primarily based on focus on the full potential of wind and solar resources to constitute a green and sustainable power system. The second is to mitigate climate change. Renewables have already been prescribed as the dominant source of power generation, officially in China's government policy. The third one is China's energy law requires the integration of wind and solar into the power system as a priority. The fourth is in contrast to other power systems, wind and solar power generation are anticipated to be the cheapest power source soon, and the marginal cost of wind and solar is near zero. The fifth, without good understandings on the potential of wind and solar alone to power China, it will hinder the holistic layout of the energy development plan. And the model constraint is that the technical installed capacity of wind and solar PV stations are greater than or equal to zero, but less than or equal to the installed capacity. The model objective function is that the deviation between the wind and solar power generation and the power load is smallest. Mathematically, the objective function and associated constraints was formulated as the following. Next, we did wind energy assessment. Energy was assessed using wind from 15 kilometers, a vertical resolution of 10 meters, and a time period of 1990 to 2016. And taking the reasonable dependence of a wind turbine power at 1 meter height were calculated using 4 onshore wind turbine power curve and 3 offshore turbine cover curve, respectively. For solar energy assessment, solar energy was assessed using solar radiation from China, resolution of 5 kilometers and a time period of 27 to 2014. The hourly solar PV power output was calculated using the model modified from Duff and Benjamin as follows. You can see from these figures. And for electricity demand, the hourly electricity load data by all society sectors were obtained from China's state grid and China Southern Power Grid. We collected realistic electrics, but only for the year of 2017. The electricity load projection is achieved by applying an annual increase rate to the realistic historical load for each province, and the increasing rate was retrieved from a report from China's Energy Research Institute that comprehensively consider factors contribute to the load projection, including economic growth rate, carbon emission, population size, technology cost, and environment protection. And for and in this study, we include grid connection, technology improvement, and demand response to promote wind and solar energy development. We accept both independent effect of each strategy and the combined effect of as a result. One, the base scenario without any development strategy. Scenario 2, grid connection. For grid connection, we assumed that each regional grid allowed flexible electrical grid are interconnected in each regional grid. Three, technology improvement. We consider the improvement in solar cell efficiency and replacement of a fixed system with solar tracking system. Scenario 4, demand response. We
Hi, Professor Wang. Maybe the internet is not very good. We can't see your screen. Hi, Professor Wang. Can you hear me? Can you hear me? The internet is not very good.
Maybe, yeah, Professor Wang, maybe you can switch off your video. Maybe the bandwidth is not sufficient for to share screen and using video. Professor Wang, you're muted.
Hi, Professor Wang.
Yeah, Professor Zheng, I can hear you.
Oh, yes. The internet is not very good. Maybe you can turn off your camera and share your screen again. Can you share
Okay.
your screen? Yeah, it's better now.
Can you see this picture?
Yes, yes, we can see your screen now. Please go on.
Yes. In this study, we combined effect of several strategies together, and all eight sorry.
Hi, Professor Wang, we can't hear you again.
He's not online.
Yeah.
Faye, do you like to wait for him?
How about we wait for him for another 2 minutes? If he still can't connect the meeting, shall we end then?
Yeah, let's wait. Yeah, 2 more minutes for him. Yeah.
Sorry, everyone. It seems like some problem happens to Professor Wang Yang's internet connection. Hi, Lee, are you there?
Oh, yep, I'm here.
Shall we end our webinar?
Yeah, so you can perhaps conclude the webinar, the event. I'm in the yep, it's fine with me.
Yeah, okay. Thanks for all the speakers today. Thank you for all your excellent presentation, and thanks for our audience here. Hope we can have more opportunities to communicate with each other. Thank you very much. If there is no questions, maybe we can end our webinar today. Thank you again, and sorry for the internet connection for the last speaker. Thank you.
Yeah, thank you very much.
Thank you.
Thank you, the organizing committee.
Thank you.
Bye.
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 Okay, so I'm stopping the recording the webinar.